Integrals by method of substitution. So step one, essentially what you're doing is reverse chain rule, or you could just say you're finding a function whose integral is also present in the integrand. So what you're essentially doing is you're looking at that integral and you're saying, if I take the derivative of this, is there another part of the integral that it's equal to this? And this is really where the magic happens, because when you get du, that encapsulates that other part of the integral and makes it easier to solve in terms of u. Step two is set that function equal to u. Step three, compute the derivative of u, and then this is just going to be du when you write it down in form. And then when you write the integral, you want to write the integral in terms of u and du now. And after you do that, you integrate with respect to u, and then you substitute back for u. So what you're doing is you just substitute what that initial value was for u. So say u was equal to like 3x plus 7. You now substitute back in that value of what u was equal to in the original, and everything should be in terms of the original variables used in the equation.
Okay, so this is going to be the first episode to my integration, or to my Calculus 2 series. So first I'm going to start off with the first unit, which is going to be integration techniques. And first one I'm going to do is substitution methods. So this is use substitution, commonly called, just solving by substitution. So first example we got here, just a polynomial. Let's look at this. So we need to find a part to be equal to u and another part to be equal to du. So when you look at this, you want to kind of have in mind what's going to be u and what's going to be du. So if you take the derivative of this first part, or you set this first part equal to u, kind of do these easier ones in your head. And, du is going to be equal to 6x plus 4, and you do this derivative. It actually has a dx on the end. Can't forget that. You end up getting u to the 5th du, and this is where you're in the u space. You're taking the derivative of everything in terms of u, so 1/6 u to the 6th plus c, don't forget that, indefinite integral. And you plug u back in the end. And that's all there is. End of the video. No, not quite yet. This is really easiest one you're probably going to see. So basically, essentially what's going on here is you want to look at it and keep in mind what looks like if you take the derivative of it, it will equal the other part. So here, I looked at this, you see 3x squared plus 4x. One thing I look out for is what has a higher exponent, especially if it is like a polynomial problem like this. The derivative of 3x squared is going to be that, and then see this 4x, that's just going to be equal to that. So you keep that in mind, and it just makes it really easy and makes it actually possible to do some of these integrals. Let's move on to a little bit more of a challenging one. Let's do a fraction. So let's say we have x cubed, x to the 4th plus 7 squared dx. And then you want to look for the same thing again. What looks like if you take the derivative of it, it will equal the other one. So if you look at x cubed, you take the derivative of this, you're going to get 3x squared. Well, 3x squared doesn't really do you any good. It doesn't cancel anything out. But if you take the derivative of x to the 4th, you get 4x cubed. The fact that you have an x cubed is in the numerator means that this is a good sign, because that will get rid of that in the numerator. So we're going to set u equal, and we'll just add in that constant, because when you take the derivative, that constant's just going to disappear. So u equals x to the 4th plus 7, and du equals 4x cubed dx. So now put everything in terms of u. So we have u squared in the denominator, we know that. And we have that dx, it's still going to be there. But here we see we only have a 1 dx, or a 1x cubed dx. So essentially this is equal, we can write over here 1x cubed dx is what we have, but we know du equals 4x cubed dx. So what we have is equal to 1/4 du. So the du calls for 4x cubed, but we only have 1x cubed. So we know since we have a fourth of what we need, that's just going to be equal to 1/4 du. So we can just pull that 1/4 out. We can then put this 1 back here. It's actually du too, not a dx here. So 1/4, and then we have this integral here, 1 over u squared. What I like to do is I like to pull that u squared into the numerator. When you do this, you have to make that exponent negative, so you get u to the -2, and then integral still 1/4 du. I just find it easier to do. Then you take the integral of this and you get negative u to the -1 du. Don't forget that 1/4 again. And you plug u back in. And you can turn it back into a fraction too here. It's what I typically do. 1 in the numerator, and then denominator is x to the 4th plus 7. Multiplied by 1/4 plus c. So yeah, that is what your answer will be. In this one, it worked kind of the same way as the first one, where you just picked out the one that had the higher power. So x to the 4th and x to the 3rd, that's just kind of how they work out. Let's go to one where that does not work out. Let's look at some trigonometry. That's not some rule, like that's not some law or anything. That's just something I look out for when I see a lot of constants in some integram like that. So this one will show you why. So let's say you have tangent of x, secant squared of x. So we're still looking for what derivative equals the other one. So just by looking at this, we see tangent of x and secant squared of x. So if I use tangent as my u, this is why it's important you don't just look at the powers, because if you did just look at the powers, you'd think this is going to be your u, but really it's going to be tangent of x. Because when you take the derivative of tangent of x, you know it's equal to secant squared of x. And this is really where the magic happens. It just u du, get 1/2 tangent of x squared. That is your answer. And do one e to the 3x dx. So our u here is going to be 3x. du is going to be equal to 3 dx. So now we have e to the u, and since du equals 3 dx, we know that this, all we have is a dx here, and that's 1/3 of what we need here. And you could also rearrange this to see that dx equals 1/3 du by rearranging all of this up here, this equation. So we can just pull that 1/3 out, put it out front of the integrand, 1/3 du. And the integral of e to the u is just e to the u, so our answer is 1/3 e to the 3x plus c.
Integral of x squared plus 1, and then e to the x cubed plus 3. Plus 3x, and then take the integral with respect to x. So this is a little bit of a lengthier integral, but this will be just as easy as the other ones. So we take u, still like what I was saying earlier with look for whatever has the highest value in the exponent, typically tends to be u. So the u I'm going to set is going to be that x cubed plus 3x. And take the derivative with respect to x, of course. It's going to be 3x squared plus 3. So now we can substitute this all in and put everything in terms of u. So that means we have u e to the u, or no, we have e to the u, but then this part out here is not the same. So we have 3x squared plus 3 here, and we only have x squared plus 1 here. So we can take a 3 out of this. Actually, this is equal to this. And then we take a 3 out of this, and we have x squared plus 1. So we know that x squared plus 1 is 3 times what we have there, so we know that we need a 1/3 out front to account for that, so it's 1/3. Let me fix this pencil. So we have 1/3 e to the u, and they're always forgetting this right here, dx, 1/3 e to the u du. Take the integral of this, e to the u is just e to the u. We have 1/3 e to the x cubed plus 3x, and then since this is an indefinite integral, it's just going to be plus c. Alright, let's try something with some logarithms in it. So let's take the integral of, let's say we have 1 in the numerator, and then 3x plus 2, and then ln of 3x plus 2. Integrate this with respect to x. So yeah, you really don't have much of a choice here. Kind of see this 3x plus 2. No, that's going to be u. So u equals 3x plus 2. Take the derivative, and that's just going to be 3. So now we put this in terms of u. So in terms of u, we have 1 over u ln of u. Well, we can't really do much with this. You know, what do we do from here? So in this case, you're going to have to do substitution again. So this is an example of a double substitution here. So we'll now use a new variable. It doesn't really matter what you use. I'm just going to use v. So we want to have the same method. We want to think, what can we take the derivative of that will equal something else in here. So if I take the derivative of 1 over u, that's not going to equal ln of u, but we know the derivative of ln of u is equal to 1 over u, so we want v to be equal to ln of u. And then, so dv is just going to be 1 over u du, just like we had thought out. So our new integral, and actually I think I forgot a 1/3 up here. Let me see. 3x plus 2, so yeah, I did forget, you need this 1/3, cannot forget that part, very crucial, very easy to forget as you can see. So 1/3, and our new integral is going to be 1/3, 1 over v dv, because this is essentially just saying, because that I can see that this is just 1 over u, this is this ln of u is just in the numerator as well. So it's essentially this, but then this 1 over u is just going to be equal to dv, so that just kind of leaves out and gets encapsulated by the dv, so we're left with 1 over v dv. So when you take the integral of this, you just get ln of v plus c and 1/3 times all that. And from here, you're still not done yet, because you need to get this in terms of, you need to get it out of terms of u and v and into terms of your original variable x. So from here, you sub v equals ln of u, so you sub for v back in. You're done integrating at this point, so that it's the natural log of the natural log of u plus c. You sub u back in, and u was 3x plus 2. So the final answer is going to be 1/3 the natural log of the natural log of 3x plus 2. And just slap a plus c in there at the end.